so I'll try the mic. So yeah, I'm going to talk to you about how intelligent, affordable robotic arms are set to transform industries. Now, if you're like most people, when you think about robotic arms, you might envision something like this, a hyper-intelligent robotic system that can do intricate tasks, working side-by-side man. The reality is very different. The reality is that robots struggle to do even the most simple tasks. And in fact, in manufacturing today, 90% of all of the tasks that could be automated are actually done by hand. We think it's robots whizzing around factories, but the reality is much more like this. It's rows and rows of people performing mind-numbing tasks for hours and hours on end. So this is bad for people. It's also really bad for business. Operating margins in this industry are anywhere from 2 to 4.5%. That's very thin. And 80% of their costs are labor. So when you factor in rising wages, foreign competition, and the fact that very few people actually want to do these jobs, they're in dire straits. So you might be wondering, well, why don't they just automate? I mean, after all, a robotic arm can do anything a human arm can do mechanically. But the problem is that they're expensive, they're dangerous, and they're an absolute nightmare to use. So to give you some specific numbers around this, for your average robotic deployment, it's going to be $133,000 per robot per task. That's 33 on the arm, another 45 on attachments and making it human safe, and then $55,000 and several weeks of downtime just to make it move. And that third part is recurring. Every time you want to change a simple task, you have to hire in your integrators who come back in, and it's another few weeks and another $55,000. And so this is really the problem that we set out to solve at Carbon. So KATIA, Kick-Ass Trainable Intelligent Arm, is about 10 times cheaper than any other robot on the market today. It's significantly safer. And our software, where the real magic happens, makes it easy for anyone to set up their own tasks. So normally we talk about the mechanics behind this and how we've been able to do that. But since this is a vision summit, we're going to talk about the software and some of the role of vision in this. So what you're looking at on the left is a traditional robotic arm controller. This is a KUKA controller. It's running Windows XP. And actually, fun fact about KUKA, to program a KUKA robot, you need to know KRL, which is KUKA Robot Language. There is a school in Michigan. You can go and get certified. But as you imagine, not many people know how to do that. So we completely rethought how we do this. And we have task-specific plug-and-play apps that essentially just work. Now, the reason you might be wondering, well, why is it so hard to program a robot? In addition to the KRL nonsense, robots are actually dumb and they're blind. So there are industrial vision systems today, and these are great for very simple operations like taking a snapshot, sending it back to the arm, where they scan or they do simple inspection where you get a quick yes, no, go, no-go scenario. But the problem, in addition to being ferociously expensive, is that they're very difficult to integrate. These are standalone black-boxed systems, completely separate from the kinematics of the robot. So to imagine what this is like, I mean, you can imagine if you were blindfolded and someone was telling you where to go and what they were seeing. You might be able to avoid obstacles, you might be able to cross a street, but you could never catch a ball, because you don't have the tight enough integration between your eyes, your brain, and your motion. And it's the exact same thing with robots. Specifically, when we're talking about robotic arms, we're not just sensing the environment, we're not just avoiding the environment, we're physically manipulating it, we're interacting with it. This means we need to understand our context, we need to reconstruct the context, we need to understand how that's changing, all the while maintaining very high speed and very high precision. In many cases, the challenges for other applications are accuracy on the order of centimeters. We're dealing with microns. And so this is a very intelligent audience, so I won't belabor the point. We benefit, like everyone else, from the reduced cost and increased speed of cameras and processors. We also benefit a lot from electric vehicles, IoT, and funnily enough, smart washing machines, which I can tell you about later if you're interested. And all of these have come together to enable us to run very fast algorithms on the device, leading to faster setup, easier, wider deployment, which in turn increases or improves our algorithms. And it's this way that we're able to get the very tight integration between hardware and software. So the first obvious application is manufacturing, for all of the reasons that we described earlier. And this is really where you're seeing the biggest push. If you've heard of Industry 4.0, advanced manufacturing, this is where the biggest investment and the biggest push is coming for smart robots. But it certainly isn't the whole story. Medical research is another huge opportunity for us. So much like manufacturing, most research today, around 10% of all published research, is actually done by hand. Many of us have either been the grad student or known the grad student who's manually pipetting in labs. And there's huge problems with reproducibility. There was a study in 2012 where Amgen tried to reproduce 53 landmark cancer studies, and they found that only 6 of those were sufficiently reproducible enough to design studies around. This is one of my favorite examples. This is a robotic arm attached to a wheelchair. This man is paralyzed, almost completely paralyzed from the neck down. He's been unable to leave his house, to open doors and to navigate the world. But with this, he's able to, for the very first time, to actually pour his own drink. And so while these might look like wildly different applications, behind the scenes, there's actually a lot that they have in common. The actions that go into pipetting in labs are very similar to what you need to dispense adhesive, and then can be reconfigured. And the key is understanding how these elements can be reconfigured and then enabling people to build on top of them. So in many cases, we're not just talking about specific industries, we're actually talking about a new type of labor. And I'll leave you with one final thought, which is humans are by nature tool builders. It is one of the things that we do best. And many of our recent inventions, computers, smartphones, the internet, have been tools for the mind. What we now have are tools for the mind and the body. And it's our belief at Carbon that by making robotic arms dramatically more accessible, we can build the foundation for a much more equitable society, one that greatly alleviates human suffering and amplifies what it means to be human. So thank you.